Okay, we're back, and I'm sorry I got interrupted, but I have a 15-minute time limit here, so we'll continue with this example. So to set this example up again, how do you find a missing force from a free body diagram given other forces that already exist in an acceleration? So in this problem, we know that the normal force and the weight are both 50 newtons. Well, that tells us that there's no acceleration up and down. This thing is not accelerating vertically at all. So then we look horizontally, and we know that there is a horizontal acceleration of 2 meters per second squared. And the frictional force, this force over here, is 20 newtons. And so the question is, if the frictional force is 20 newtons and it's accelerating at an acceleration of 2 meters per second squared, what is this missing force? Well, in the x direction, and this is the equation we're going to use, that missing force minus our frictional force is equal to ma. So our missing force is equal to ma plus the frictional force. So that equals our mass. Okay, so what is the mass? If the weight is 50 newtons, then the weight equals mass times gravitational acceleration. I don't know if you know that yet. That might be coming in the next unit. So in your problem, you're probably given the mass. But anyway, weight equals mg, and so the mass is weight over gravitational acceleration. And in this problem, that is 50 newtons divided by 9.8. 10 would be a good estimate, but I'll use 9.8. So 50 divided by 9.8 equals 5.1 kilograms. So now we know the mass. So the unknown force equals 5.1 kilograms. Again, you'll probably be given that in your problem, times the acceleration, which is 2 meters per second squared. Sorry again about my tablet. It's an S. Plus the frictional force, which is 20 newtons. So 5.1 times 2 plus 10.2. I could have done that in my head. 10.2 plus 20. That means I have an unknown force of 30.2 newtons. Okay? So make sure that you study that problem, and because you're going to see something like that on the test, finding that unknown force from a free body diagram. Okay, now we're going to move on to the third part, what should have been the third video, but this will be the rest of the third video. Newton's third law, action reactions. So Newton's third law, everybody knows it. For every action, there is an equal and opposite reaction. But what does that really mean? What it really means is every force is an interaction I can't spell, between two objects. So one object doesn't just act on a second object, the two objects act on each other. So if I have object A and object B, object A exerts a force on object B, and at the same time, object B exerts an equivalent force back on object A. So if I have a bug and a car, and the car hits the bug while it's driving, the bug exerts a force on the car, and the car exerts a force on the bug, and the forces that they exert on each other are equal. Now, the accelerations that happen because of those forces are very different. The moon and the earth pull on each other with exactly the same force. The moon is affected more. The moon's acceleration is more than the earth's because its mass is small. But when two objects interact, the forces that they exert on each other are the same. You need to be able to identify action reaction pairs, and that would be taking a force and stating it as a force between two objects. So, for example, the gravitational force between the moon and the Earth. So the Earth pulls on the moon, and the moon pulls on the Earth with the equivalent force. So they are pulling on each other, and they're pulling on each other with the same force. And this is an action-reaction pair. The Earth is pulling on the moon, and the moon is pulling on the Earth. Action-reaction pairs always involve more than one object. They always involve a pair, two objects. So if you're sitting down right now, you're pushing down on your chair, and your chair is pushing up on you. So you and the chair are interacting. You are pushing on the chair is pushing on you. It takes two objects, two different objects pushing on each or acting on each other to have an action-reaction pair. The acceleration that these forces cause can be different. And let's look at an example of that. Let's say we have a cannon, and it has a mass of 100 kilograms, and we have the cannonball with a mass of 10 kilograms. And let's say that the force that they exert on each other is 50 newtons. Find the accelerations. So we know that acceleration is equal to force divided by mass. So for the cannon, we have acceleration equals 50 newtons divided by 100 kilograms, and that equals 0.5 meters per second squared. And for the ball, oops, I didn't undo my, there we go. For the ball, we have acceleration equals F over m equals the same 50 Newton force divided by, now the mass is only 10 kilograms, and that equals 5 meters per second squared. And so you can see that same force causes a different acceleration in the objects depending on their mass. Now, what will you have to do with this? You'll have to work a problem that's similar to that. Let's change it up just a little bit, but we're still going to have a cannon and a cannonball. Let's say we have a 100 kilogram cannon and a 10 kilogram ball that is accelerated at 10 meters per second squared by the force that the cannon and the ball exert on each other. And the question now is, what is the force between the cannon and the ball? No. Okay, and then, I forgot, there are two parts. And what is the acceleration of this cannon? Okay, so to find the force, we're going to have to find the force on the ball, and it's equal to ma. And that equals, the mass of the cannonball is 10 kilograms times the acceleration is 10 meters per second squared. And that is equal to equals 10 times 10 is 100 newtons. Well, that's the same. The force acting on the ball is the same as the force on the cannon. So we know the force on the cannon is also 100 newtons. Now, if I want to find the acceleration of the cannon, its acceleration is equal to force divided by mass. So it's that same 100 newton force divided by the mass now of the cannon, which is 100 kilograms. And that equals 1 meter per second squared. Okay, and that actually is the end of our review. I hope that you find this helpful. I promise you that if you go through it carefully and you pay attention and take notes and go back and study stuff that isn't familiar to you, that this will help you to do better on the test over Newton's laws. Thank you.